Asli bin Azman from Group 1K, Chemical Engineering Group 1 from the January 2020 semester. In this semester, we have given a task to perform an integrated project. The members of our group would be myself, Hamifah Asli bin Azman, Hanan Shahira binti Muhammad Azmi, and also Nurhani Suraya binti Basiruddin Shah. Okay, for our integrated project, we were tasked to design a SMR technology to produce 30,000 tons per year of hydrogen with a purity of 99.9% from natural gas and steam. The SMR technology consists of a SMR reactor, CO2 removal unit, and also a H2 purification. We will be doing this project using the knowledge that we were taught in reaction engineering process 1, and also
This one will be covering the reaction engineering part. There are two types of reactors involved in reaction engineering, which are SMR and also WGS reactor.
The first reaction is endothermic steam methane reformer (SMR) process at 20 to 35 atm, and it takes place in high temperature 800 to 1000 degrees Celsius. Methane is reacted with steam producing carbon monoxide and also hydrogen. The subsequent reaction would be exothermic gas water shift (WGS) process, which takes place in lower temperature 200 to 400 degrees Celsius and medium pressure 10 to 15 atm. The overall equation is in positive value, which is 165 kJ per mole. Thus, the overall reaction can be considered as endothermic reaction.
Both of the processes occur in the same PBR reactor. PBR reactor is used as it is equipped with bed catalyst. Catalyst used for SMR process and WGS process is the same. It is 18 weight% of nickel supported by aluminum oxide.
The stoichiometric table for SMR reaction. From Joule, the conversion of methane is 0.93, and hence you can calculate the value of flow rates as the flow rate of hydrogen produced is stated, and then we can calculate other values and fill in this box. The first side product, carbon monoxide, will be the reactant for WGS process and will react with excess steam. Hence, we can calculate the other subsequent values in the stoichiometric table of WGS process.
From journals, the reaction order for SMR process and also WGS is 1. Since K01 and K02 is given in the journal, so we can calculate the K1 and K2 using Arrhenius equation.
Reactor sizing. This is the formula for volume. Weight of catalyst will be calculated using this formula. Hence, we can get the PBR volume.
So now let's move on to selectivity of reaction. We would use two kinds of formula in finding selectivity, which are hydrogen selectivity formula and also overall selectivity formula. So for the equation of hydrogen selectivity formula, the formula would be the outlet molar flow rate of hydrogen over the outlet molar flow rate of methane plus the outlet molar flow rate of hydrogen. So for the overall selectivity formula, the formula would be the flow rate of desired, which is our hydrogen, over the outlet flow rate of undesired product, which is carbon monoxide and also carbon dioxide, depends on the reactors that we are using. So for the SMR reactor, our hydrogen selectivity is 0.9755 and the overall selectivity is 2.999. So for the WGS reactor, the hydrogen selectivity would be 0.9738 and the overall selectivity would be 2.999. So now we are moving on to the yield of reaction. So for the yield formula, we will use the same formula for both of SMR and WGS reactor. So the formula is the outlet molar flow rate of hydrogen times with the molecular weight of hydrogens over the molar flow rate of methane into the reactor times with molecular weight of methane. So for the SMR reactor, our yield would be 0.1744 and our WGS reactor yield is 2.3168. So based on our research paper and journal, we found out that yes, the yield should be lesser than 1 because 1 is the maximum yield for the reactor. But if the product contain impurities, so the yield can be more than 1, and that is what we have for now. So we are at the strategy to maximize production of hydrogen. So according to S.Z. Abbas, there would be few strategies to achieve higher production of hydrogen, and the factors are temperature, pressure, and steam-carbon ratio. So for temperature, the change in temperature will affecting the heat of reaction. So in SMR process, increasing temperature to equilibrium and beyond will result to the rise of purity and yield of hydrogen product as conversion of methane increases as well. But however, for the WGS process, beyond the temperature of peak yield, the purity and yield of hydrogen will decrease as temperature increase. So we will conclude that maintaining ideal temperature for both SMR and WGS reaction is necessary in order to maximize the production of hydrogen. So now we are at the second factor, which is pressure. So as stated in Le Chatelier's principle, the low pressure is favored in SMR process as the number of moles of product generated is higher than the number of mole reactants. So decreasing pressure will result to the rise of conversion of methane and also to higher production of hydrogen, but contradicting to WGS process as it is a cumular reaction. So the change in pressure will not affect the process once equilibrium is achieved. So the last factor would be the steam-carbon ratio. So as the steam-carbon ratio increases, the conversion of methane is also increases. But however, as steam-to-carbon ratio increases, high amount of energy is required to produce steam and eventually will reduce the rate of conversion and increase the operational costs. Thus, it is important for us to maintain ideal steam-to-carbon ratio to maximize the hydrogen production.
For the type of absorbent to be used in our design, after various research, we have found that the best absorbent would be the T-type zeolite with the aid of activated carbon in a multi-layer column design. The T-type zeolite has high absorption during PSA or pressure swing absorption in ambient temperature. The reason being is because the nanostructural crystalline in aluminum and silicon atoms exist in tetrahedral form. This makes the T-type zeolite have cavities and also channels to absorb component. However, the size of the columns are too small to absorb a more bigger component such as methane and also carbon monoxide. So we use activated carbon to remove these other components. In our slide, we will be showing the picture of zeolite and also activated carbon with their. For the type of isotope that we chose for our design would be the Langmuir-Friedrich equation because we are using multi-component absorbance in our design. The equation for the Langmuir-Friedrich equation would be Q equals to Qm Kp to the power 1 over m over with Kp plus 1 to the power 1 over m. In our slide, we'll be showing you the graphs and also the data of the absorbance to fit the Langmuir-Friedrich model. The reason being of choosing this isotherm would be as it produces good reproduction of data. Next, the diagram in our slides would show you the sequence of steps of our 4-column PSA cycle. This method would be very efficient to provide us of hydrogen with a purity of 99.9%. For 4-column PSA cycle, it has been found that there would be a sequence of steps to be followed, which is the adsorption, depressurizing equalization 1, provide purge, depressurizing equalization 2, blow down, receive purge, pressure equalization 2, pressure equalization 1, and also the backfill step.
The next part is upscaling the process. These are the data obtained by research from articles. First step is calculating total volume of adsorbent. This is the formula of volume of column. The total volume we got is 4 meter cube. The assumptions our column is packed with adsorbents, 55% filled with BPL activated carbon and 45% is filled with T-type zeolite. Next is finding volume occupied by adsorbent, which we can get by multiplying the composition of PPL activated carbon and T-type of zeolite with total volume of column. And we have to find the mass for each adsorbent in the column by using this formula. The mass of production of hydrogen per year calculated is 576.66 tons per year, which is lesser than 30,000 tons per year. Hence, scale up is required to reach target production of hydrogen yearly. These are the manipulated variables for scale up. The new total mass of adsorbent calculated is 235936 kg and the total volume is 208.1 meter cube. To find the length of column and the diameter, we need to combine equation 1 and equation 2. The diameter calculated is 2.98 meter and the length is 29.8 meter. Since we have TT, TB and the HT is remain constant, we can calculate the HU and B. So next is mass balance. These are the data that we got. The amount of CO produced calculated is 2.1 tons per year. Inlet mass flow rate of hydrogen is 1.1 kg per second and the total mass flow rate is 1.45 kg per second. Then we can calculate the mass flow rate of inlet CO, CH4 and also CO2.
So in conclusion, for reaction engineering part, we have explained about two types of reactors, which are SMR and also WGS reactor. Using stoichiometric table of WGS and also SMR, we can calculate the mole flow rate and also the concentrations. And also we can find yield, selectivity and also reactor sizing. To conclude the RE part, there are three factors that affect hydrogen production, which are temperature, pressure, and also steam to carbon ratio. For sample part, the design had achieved 99.9% purity of hydrogen production at 30,000 tons per year using T-type zeolite and also activated carbon. The design for PSA process chosen was 4-column PSA cycle. A lot of calculations were made and finally hydrogen production of 30,000 tons per year with purity of 99.993% is achieved.
For reaction engineering, we need to find the description of the reactors in terms of operating condition, mass balance, selectivity, and the yield of reaction for SMR and also WGS. Hydrogen and other materials such as live methane, carbon dioxide, carbon monoxide, and water were sent to another purification unit, which is carbon dioxide adsorption unit and also hydrogen enrichment unit. The purification unit ensures the end product contains hydrogen with a 99.9% purity and remove all the impurities before purification process begins. An adsorbent and isotope model has been chosen through multiple and critical research. The PSA method was used to remove impurities with a chosen model of 4-column PSA design.
We think that this project is quite interesting, but it was quite hard as well. However, we learned so much things. We learned that we need to be hardworking and to communicate well with our team members in order to solve all the problems. Okay, for the evaluation reflection, for RE part, we had some difficulties in solving the problems. This is because it's slightly different from what we learned in class and more challenging as well. But with teamwork and hard work as well, we managed to solve our problems.
So now we are at analysis part, and the question is, what sense can you make of the situation? So we learned that cooperation and consideration between members are highly emphasized as a motivation for us to complete the project. So we should have considered other members and us, whether they need help or maybe they have difficulties, and we should not just wait for them to give the instructions. As well as all members should have the sense of responsibility and not letting others to feel demotivated because of the bad attitude. So they should also have the sense of wanting to learn something new and not just asking for others to teach us from scratches, from A to Z. We should know by our own before we ask something that we didn't know. Yes, we are free to ask for help and advice, and we cannot done it alone. Yes, that is necessary. So for the conclusion, the question is, what else could you have done? So other than that, we should also have good connection with members from others team. Yes, this might look like a simple thing, but we should make it important because this is to widen our perspective and also to add more brilliant ideas into our project so that we can get a project that is produced from various aspects holistically. So we should also refer to our lecturers a lot because we want to meet their expectation and we want to present a good quality of project for them, to them. So the last would be action plan. If it rose again, so what would you do? So in our opinion, we will let the members know the expectation of the outcome of the project, and we should also let them know that they should give cooperation and we should help each other so that we can be more proactive in our group. So we should also be transparent with each other, give honest feedback, give honest advice, and also correct any mistakes that they have done so that we can improve our work quality together.